So gene expression index is the next thing. After the data is normalized, we need to look at the expression index. Remember the original array design. We have a probe set of different probes. They are located on different corners or different locations on this array. This is just in case if you have a bubble in the hybridization. You don't lose this whole gene, right? Like you just get rid of one probe. So they are kind of in different locations. The mismatch and perfect match are usually right next to each other. And so we usually have 10 pairs of numbers or 20 pairs of numbers. At the end, what biologists care about is a single number. How much is this gene expressed? So how do we summarize these 10 or 20 pairs of numbers to come up with a single number? Expression index is that gene expression level that people care about. So most of the time, if you look at the perfect match probes, this is just one sample, different probes, and the blue is the perfect match probe, red is the mismatch probe. Remember, originally, we were hoping that the mismatch probe measures background noise, so it should have signal lower than the perfect match probe. But you can see sometimes there might be some other junk or whatever hybridizing to this location, which makes the signal even higher. So it's kind of tricky. So how do we, supposedly you are the computational biologist in 1996. Affymetrix just had this array, and your collaborator bought the array to do their experiments. They got some data, and there was not any algorithm available. They came to you. What can you do to help them? You say, oh, can you give us the expression level of every gene by summarizing this 20 numbers, 20 pairs of numbers for each gene? Can you come up with something? Yes.
We usually subtract the perfect match and mismatch and
rank them. Okay. Are they supposed to measure the expression of the same gene? Same gene? So instead of ranking them, maybe you average them, right? You think, okay, they probably average. So indeed, that's what Affymetrix did. They have a microarray analysis software. The idea is, you can see, so all the probe, for this probe set, they do a PM minus MM. They summarize this and they divide by the total count. And it turns out at the end, they have to remove some of the pairs because the first thing they did is they realized there are some probes that are not so great. Later on, actually, Affy have learned which probes have very crazy behavior. They just remove them. In the later design, they just have the good performing probes. But in the early days, they say, oh, let's remove the highest, remove the lowest. The remaining one, they calculate average. They also calculate a standard deviation of the different probe pairs. And then they say that eliminates those probes where the PM minus MM value is 3 standard deviations away from the probe. So even though they started with 20 pairs, at the end, it could just be 15 pairs that end up being used, or maybe even fewer. One problem with this is it's a very naive algorithm. You can really eliminate about 30 to 40% of the probes on the array, and occasionally you might end up getting a negative value, which means even removing the outlier, the average of the remaining probes give you a minus 0.1 expression. 0.1 expression, which is very inconvenient because the gene is either expressed or not expressed. It can't be a negative value, right? And so that's where statistics really came to help. There are a number of generation of algorithms developed. We will just talk about the most popular one. And this is the method developed by Rafael Irizarry. At the time, he was at Hopkins, but now he's at Dana-Farber Cancer Institute and Harvard. A biostatistician, and Terry Speed is a statistician who also developed the quantile normalization. So RMA stands for robust multi-chip analysis. And these are the few steps. We'll talk about the steps separately. The first step is background subtraction. So if you look at all the probes on this array, you realize that there are real signals, but there are some also very basic noise. If you look at the whole array, you can roughly estimate what's the baseline, because there's a lot of dark spots that have nothing, but they still give you a little signal. Okay. Usually, based on the data, the RMA discovered that the real signal is an exponential distribution, which is like this. This is like this, is like that, and so the exponential distribution is like this, which means a lot of genes maybe not expressed. Some genes express a little bit. Few genes are expressed at a very high level. The background is usually considered to be a normal distribution. I'm trying to find my mouse again. Sorry, can't find my mouse. Oh yeah, there it is. Okay, clear. All drawings. Stop. Okay, so now I have my mouse back. Yeah, so the signal people believe is exponential distribution. The noise is kind of normally distributed. And so if you are given the original PM value, you believe is there is the real signal plus some noise, and there is a strict solution for this you can actually solve. So given the PM probes, you can look at all the probes on the array to estimate the background level and subtract that out. Then assuming that the real signals are always positive, then you can estimate the rough signal level. Okay, so this is done array by array. So if that array is overall very bright, that will just get also removed. Okay, so yeah, so this is performed on each array separately, and then every probe location will have a signal. And the key for this multi-array analysis is you can look at the signals. This is one gene. The blue lines here represent, so this top line is the probe value coming from one sample on this gene. And the bottom is the same gene on a different array, a different replicate or a different sample. So you can see, and the bottom are the mismatch probes. You can see that this probe in general have much higher values, and they also have a pretty high variance. And this probe in here, it has a low value and a low variance, but overall the ranks of the probes are more or less stable, which means even if the probe value is low, and it can even be lower than, you look at this one, the perfect match probe, you know, most of the lines you can see they preserve their rank, but this perfect match probe still have lower level than the mismatch probe. Maybe that mismatch probe gets cross-hybridized to some other locations you don't even know. And so RMA decided we're not gonna even bother with the mismatch probe. We're only going to look at the perfect match probe, but to learn the behavior of the different probes by looking at how this probe behave across many samples at the same time. You can learn the trend of the different probe, their behavior, okay? Can you guys guess what is the, yeah, so actually I'll just say this. Each probe signal is believed to be proportional to two things. One is the amount of actual RNA or cDNA, or how much this gene is expressed in that particular sample. And that's what you want to measure, right? You want to estimate. And then the other factor that influences the probe signal is the affinity, or how good this probe is at measuring that expression level. And you can clearly see different probes have a different behavior. Can you guess what is making the signal being different? Now, why is this probe behaving so different from this probe? Can you guess? Yeah. Yes, it's the GC content. Yeah, usually if you have very low GC, the probe will have a low signal and also low variance. But if you have like 25 nucleotide, if it has like 20 GC, you'll have a high value and high variance. In the early days, people didn't really look into this. They just used multiple samples to estimate this. So before we can look at all the samples together, there's one step that is also important. We want to average, or at least we want to calculate the expression level by looking at all the samples, but we also kind of want to look at the noise. Ideally, you want to estimate the expression of a gene, which is this value, by looking at the probe behavior, allowing that different probes have different noise. So we have to understand what is the noise level. So you can see here, this probe have low value, but also low noise. This probe has high value and high noise. In fact, you can see that the x-axis is the average signal, and the y-axis is the standard deviation. You can see when the probe signal is low, the standard deviation, the noise is also small. But when the signal is very high, the standard deviation becomes also higher. Therefore, if we just average all the probe signals, what's going to happen is that the probes that have the high variation will really dominate, whereas the probes that are in the low levels, they almost never play any role, right? However, if you look at this probe, you can see because it somehow preserved the rank, that signal is still useful. We want to still consider it, even though the value is low. And so the way we do this is to take a log of the original probe signal. Then you can see then the noise level, I mean, it's not a perfect smooth like a line straight, but it's still much better than this slope in here, right? And this step kind of stabilizes the noise a little bit. Now, if you want to identify an expression index that minimize the error, then the probes that have low value versus the probe that have high value will be considered at similar emphasis in some sense, okay? And so, yeah, so we are assuming the noise is comparable on the log scale. I mean, it's not perfect, but it's pretty good. And so this is how RMA work. Remember, we are assuming that the PM value of this, yeah, so I have a mistake in here. Sorry. It should be I. So I is the sample ID. J is the probe ID. And so the PM value of sample I on probe J, initially we believe is related to the concentration of the transcript in the I sample multiplied by the probe effect on the J's probe. Let me move this a little lower so you can see the difference a little better. And so you can see the I and J a little better. Plus some little noise in here. If we take a log, remember, if you just do this, then the probes that have high values with high noise, they will dominate. And so in order to really make sure we consider all the probes, we take a log. And once you take a log, you say the log PM value is equal to the log of the concentration plus the log of that probe effect, okay? Yeah, so now we have a probe value. At the end, this is what the model looks like. Yeah, so AI is really the first part. It's the expression index that we try to estimate for this gene at this sample. BJ is the probe effect at this probe or for this gene. And plus there's some noise in the data, right? And before you do the estimation, first we need to do the background subtraction array by array. And then we take a log of all the data, and then we do quantile normalization. So first, array by array, we do background subtraction, and then we take a log of the signal value, and then we quantile normalize across different arrays, and then we try to estimate the alpha, the expression index, the probe effect, and the final noise. The way RMA estimates the alpha, the expression index, and the probe effect is kind of iterative using an approach called the medium polish. I will show you how the medium polish is done with an example. It's a very fast and robust ways, and it's efficient and robust to outliers. When you have large data set, very quickly you will get a correct result. But how do we do this? Let's imagine this. Say the statistics department have 10 professors, and they teach different courses, but it's always the same group of students taking those courses. And at the end of the day, you want to know which professor can teach well and which don't teach well, assuming that some students are good students or they rank the professors harsher than other students, right? So you can imagine the professors are the expression index you want to estimate, and the students are the probes that are doing the measuring, right? So you can imagine how this is done. It's like, assuming initially all the students are equally good, we just average the student ranking for each professor. And then you get an idea of how the professors teach. Then you use the average professor score to evaluate your probe or your students to say, that student always grade all the professors harsher. You need to adjust. Or that student is giving all the professors a good score, then we need to somehow adjust, right? So we give a student a different weight in some sense. And based on this adjusted value, we will then reevaluate how they rank the professors. And then you iterate. And at the end, you will know, okay, how the students behave. You will also know how the professors teach. And that's how roughly RMA works, okay? Before we move to the example, are there any questions about this, like this RMA approach, looking at multiple array samples at the same time, doing the background subtraction on the array to get the real signal? You do log transform to make sure the noise across different probes are more or less comparable. Then you quantum normalize different samples. Yes, question? Yeah, so at the end, the mismatch probes were not considered. In fact, because of RMA, in the later Affymetrix design, Affy decided not to design mismatch probes anymore. The background, they just look at the overall signal. It's like if the overall probe signal like that, and then the noise they assume at every location is kind of normal, and they can estimate the parameters for the exponential and the 2 parameter for the mean and the standard deviation for the background. And then given any probe value, it will give you the estimated signal, subtracting the noise. Okay. Yeah, so because of this, later on, Affymetrix no longer design mismatch probes, which save them half of the space on the array to investigate more genes to get an even more accurate readout, which is great. So we'll